There is a star you can see with your naked eye tonight. Walk outside, tilt your gaze toward the southern sky, and find the one that burns with a steady, yellowish-white fire, brilliant enough to rank as the third brightest star in all the heavens. It has been there every night of your life, every night of your parents' lives, every night since the first human looked upward and wondered what exactly is burning up there. We have stared at it for thousands of years, and in August of 2024, for the very first time, we pointed the most powerful space telescope ever constructed directly at it, and found something we did not expect to find. That star is Alpha Centauri A. It sits 37 light-years from our Sun, a number that sounds reassuringly close until you do the arithmetic and realise that 4.37 light-years is approximately 41.3 trillion kilometres of cold, dark, empty space, the nearest, the most studied, the most mythologized stellar neighbour we have. And yet, until 2024, we had never truly looked what the James Webb Space Telescope found there. A faint smudge of infrared light, more than 10 zeros and times dimmer than the star itself, sitting precisely where no artifact and no galaxy had any business sitting, has sent ripples through every department of planetary science on Earth. Not because the answer was terrifying, because it was so close, because the implications are so enormous, and because, even now, after the papers have been published and the press releases have gone out, and the community has taken a collective breath, nobody is quite sure what it means. Here is what we know, here is what we don't, and here is why one blurry dot next to the nearest star might be the most consequential thing any telescope has ever found. Imagine, for a moment, that you have lived your entire life beside a famous building. You walk past it every single morning. You have read every published history of it, every architectural survey, every memoir by every person who ever lived within its shadow. You could describe its silhouette from memory. You know its address, and yet, somehow, through all those decades of proximity and scholarship and careful attention, you have never once opened the front door and looked inside. That is the relationship that astronomy has had with Alpha Centauri. The system is not merely our closest neighbour in space. It is the only stellar neighbourhood outside our own that has ever been seriously discussed as a destination for interstellar travel, as a target for the first probe we might send beyond our solar system, as the logical first address to check in any serious search for life beyond Earth. The name itself has a weight in the culture of space exploration that few star names carry. Science fiction writers placed civilizations there. Engineers at breakthrough initiatives sketched out laser-powered light sails that might reach it within 20 years, travelling at 1/5 the speed of light. The name Alpha Centauri sits at the very centre of humanity's interstellar imagination, and yet, for all of that, until 2024 we had never actually managed to get a clean look at whether it had any planets. To understand why, you need to appreciate two things simultaneously. The first is the extraordinary difficulty of finding planets around any star. The second is the extraordinary difficulty of finding planets around this particular star. The general problem is one of contrast. A star like Alpha Centauri A, a G-type star almost identical to our own Sun, with 10788 solar masses and 2175 solar radii, shines with an absolute ferocity that dwarfs anything orbiting it by a factor that is almost unimaginable. If you could stand at a safe distance and watch our own Jupiter passing in front of the Sun, the dimming you would observe would amount to roughly 1% of the Sun's total light. And that is one of the easiest planetary signals we know how to detect. Finding a planet by direct imaging, meaning actually photographing the planet as a separate point of light beside the star, is the hardest trick in observational astronomy. You are, as one astronomer memorably put it, trying to photograph a firefly hovering beside a searchlight from several miles away. Not just see the searchlight, see the firefly. While the searchlight is on, now add the specific complications of Alpha Centauri. Alpha Centauri A does not orbit alone. It is locked in a gravitational embrace with Alpha Centauri B, a slightly smaller and cooler K-type star, the two of them tracing an elliptical orbit around their shared centre of mass with a period of 79.91 years and an eccentricity of 0.52, meaning they swing between 11.2 astronomical units at closest approach and a full 35, 6 astronomical units at their most distant separation. The two stars are, at the time of most recent observation, somewhere in the intermediate range of that arc, currently sitting roughly 7 to 8 arc-seconds apart as seen from Earth. That separation sounds comfortable until you try to block the light of one star with a coronagraph, a specialised opaque mask inside a telescope designed to suppress a star's glare, while the second star blasts its own photons all over your detector, contaminating every pixel in the region where a planet might be hiding. This is the blinding problem. It is not metaphorical. When JWST's mid-infrared instrument, known as MIRI, pointed toward Alpha Centauri and deployed its coronagraph to cover Alpha Centauri A, the instrument still had to contend with Alpha Centauri B, shining at full brightness somewhere in the same field of view, unocculted, unfiltered, casting its own diffraction spikes and ring patterns across the very zone the team was trying to inspect. To perform any useful analysis of the light around Alpha Centauri A, they had to model and subtract not just Alpha Centauri A's residual scattered light, but also the PSF, the point spread function, the characteristic smear pattern of Alpha Centauri B. And because the two stars are in motion relative to each other, the position of Alpha Centauri B's PSF on the detector changes between every observation epoch. Every time you look, the noise source has moved. This is not a problem any other high-contrast imaging program has ever had to solve quite this way. Add to that the brightness of the system overall. Alpha Centauri A is the third brightest star in the night sky. Webb was not designed for this. Webb was designed to find the faintest objects at the edge of the observable universe, early galaxies whose light has been travelling for 13.5 billion years and has been stretched by cosmic expansion until it arrives in the infrared range that Webb was tuned to detect. Turning Webb toward a star this nearby and this bright is a bit like taking a radio telescope calibrated for signals from the edge of the cosmos and pointing it at a neighbour's stereo system. The instrument is not broken, but it is being pushed in a direction it was not engineered for, and the operations team at the Space Telescope Science Institute had to design an entirely custom observing sequence just to make this possible. That extra effort, as the paper's co-first author Charles Beichmann would later say, paid off spectacularly. But it was a long road to getting there, because the most remarkable thing about Alpha Centauri's planetary status, as of 2024, was not that the question was unanswered. It was that the question had been asked, and answered wrongly, before, with enormous fanfare and subsequent embarrassment, and the scientific community was, understandably, carrying that scar. This is the first open question you need to hold in your mind as we proceed. If Alpha Centauri is so close, so studied, so important to us, why did it take this long to even try a serious direct imaging search? And what happened the last time someone thought they had found a planet there? The date was October 16, 2012. The journal was Nature. The lead author was Xavier Dumusc, then a researcher at the Geneva Observatory, working with the HARPS instrument, the high-accuracy radial velocity planet searcher, mounted on the 3.6-metre telescope at La Silla Observatory in Chile, and the headline was everything the world had been waiting to hear for decades. Astronomers had found an Earth-mass planet orbiting Alpha Centauri B. Let the weight of that sit for a moment. An Earth-mass planet, around the nearest stellar system to our own Sun. The announcement sent a convulsion through the scientific community and through popular science media that is difficult to overstate. This was, if true, the single most significant exoplanet discovery in history. Not because it was in the habitable zone, it wasn't. Orbiting at a distance of only 0.04 astronomical units with a period of 3.24 days, far too close to its star for any liquid water, but because its existence meant that small, rocky Earth-class planets formed easily and naturally even in the complicated gravitational environment of a binary star system. If Alpha Centauri b had one such planet hugging its surface at this scorching proximity, who was to say there weren't others, farther out, more temperate, perhaps habitable? The planet was named Alpha Centauri b. It entered the textbooks, the press releases, the speculative articles. It became the opening scene of the 2013 film Oblivion. It lodged itself in the public imagination, with a tenacity that even most scientific discoveries never achieve. And then, quietly, and with the particular discomfort that accompanies a retraction in a high-profile field, it began to fall apart. The radial velocity method that JWST and his colleagues used works by detecting the tiny wobble that a planet's gravity induces in its host star. As a planet orbits, it pulls the star slightly toward it and then away, and that motion, utterly invisible to any telescope capable of imaging the star, shows up as a periodic Doppler shift in the star's spectral lines. When the star wobbles toward us, its light is slightly blue shifted. When it wobbles away, slightly red shifted. By measuring those shifts with extraordinary precision, you can infer the presence of an orbiting body. The HARPS instrument was, and remains, one of the most sensitive radial velocity spectrometers ever built, capable of measuring velocities as small as a few centimeters per second. But Alpha Centauri b is a star, and stars are not quiet. Their surfaces are seething with magnetic activity, stellar spots, convection cells, and oscillations that all produce their own radial velocity signals. Noise that looks superficially like a planet's signature. Separating the planetary signal from the stellar noise requires careful statistical modelling, and in the case of Alpha Centauri b, it turned out that the apparent 3.24-day signal was sitting almost indistinguishably close to a known systematic artifact in the data processing pipeline. When the analysis was redone by independent teams, Hatzis in 2013, Rajpal and colleagues in 2016, and others, the evidence for a real planet collapsed. The false alarm probability of the signal was too high. The planet, most likely, was not real. What JWST and colleagues had found was a ghost in the noise. The retraction of Alpha Centauri bb was handled with more grace than such episodes sometimes are. JWST himself published a correction acknowledging the reanalysis. The community absorbed the lesson. Radial velocity detections in active stars require extraordinary care, and the desire to find something historic must never override the cold arithmetic of signal-to-noise. But the episode left a mark. Alpha Centauri had now been the setting of one of the most celebrated false detections in exoplanet science's short history, and the next team to claim a planetary detection there was going to face heightened scrutiny, which makes what happened in 2019 all the more important and all the more tantalizing, because the next candidate came not from the wobble of a star, but from a photon of light that had no business being where it was found. The project was called Naye, New Earths in the Alpha Centauri region. It was a collaboration between the European Southern Observatory and Breakthrough Watch, the planet hunting arm of the Breakthrough Initiatives program. The instrument was VSER, the VLT imager and spectrometer for mid-infrared, mounted on ESO's Very Large Telescope in the Atacama Desert of Chile. And the plan was audacious. Spend 100 hours of VLT time imaging the habitable zone of Alpha Centauri A in the mid-infrared, the wavelength range at which warm planets radiate most of their energy, and see what could be seen. 100 hours on a world-class telescope is not a trivial commitment, the equivalent of more than 4 continuous days of telescope time at an observatory where every hour is competed for by hundreds of astronomers with proposals that have passed rigorous peer review. The Naye campaign in 2019 was a deliberate, full-throated attempt to answer the question definitively. The resulting paper, published in 2021 in Nature Communications and led by Kevin Wagner of the University of Arizona's Steward Observatory, reported the detection of a candidate point source, designated C1, at a separation of approximately 1.1 astronomical units from Alpha Centauri A. The flux was consistent with a planet of at least 300 Kelvin surface temperature and a radius of at least 3.3 Earth radii, a world somewhere between the size of Neptune and Saturn. Or, the team cautioned it could be thermal emission from a disk of warm dust arranged in roughly 60 times the density of our solar system's zodiacal cloud. Wagner and colleagues were careful not to overclaim. They reported what they saw, acknowledged the alternatives, and noted that confirming or ruling out the artifact hypothesis would require more data. More data, unfortunately, was not immediately forthcoming. The VLT had its own technical constraints. The COVID-19 pandemic disrupted astronomical programs worldwide, and the object C1 was not clearly redetected in the limited follow-up that was possible, so there it stood when JWST began its science operations in 2022, a 2019 candidate unconfirmed, with a name and a position and a faint suggestion of reality. 2 hints separated by 4 years and 2 different instruments and 2 different wavelength regimes, both pointing toward the same general region of the same habitable zone. And a world-class telescope now in orbit, with a coronagraphic capability that could, in principle, finally settle the question. But settling the question was going to require solving a problem nobody had ever had to solve before. This is the second unanswered question you need to carry. Is the candidate from 2019 real, and could the same object be what Webb found in 2024? And if both detections are fragments of the same truth, what exactly are we looking at? Webb was not supposed to look at Alpha Centauri this soon. The original timeline for JWST observations of the Alpha Centauri system was cautious, almost conservative. The telescope had barely begun its science operations when the first attempts to point it at the nearest star system ran into a problem that nobody, despite years of pre-launch modelling, had fully anticipated at operational scale. Alpha Centauri is too bright, too close, and too complicated to simply point at with standard protocols. The initial 2023 attempt to observe the system produced data that was, in the blunt assessment of the science team, unusable. To understand what went wrong and why fixing it mattered so much, you need to understand how a coronagraph aboard a space telescope actually works, because the mechanism is both elegant and punishingly precise. Webb's mid-infrared instrument, MIRI, contains a coronagraph based on a device known as a 4-quadrant phase mask, or 4QPM, rather than simply blocking a star's light with an opaque disk, the approach used in classical coronagraphy since Bernard Lyot invented the device in 1931 to observe the solar corona. The 4QPM works by splitting the focal plane into 4 quadrants and introducing a half-wave phase shift between adjacent quadrants. Light from a star positioned precisely at the centre of the mask undergoes destructive interference with itself and effectively cancels out. The star's light is not blocked. It is made to disappear by having its own waves fight against each other. What remains visible in the surrounding region is any companion source, a planet, a disk, a background object that is not centred on the mask and therefore does not experience the same destructive interference. It is a profound piece of optical engineering, and it works. MIRI's coronagraph operating at 5 microns, a wavelength in the mid-infrared that falls between the capabilities of most ground-based instruments, can in principle suppress starlight to a contrast ratio of around 1 part in 10,000 at separations of 1 to 3 arcseconds from the target star, which means it can in principle reveal objects more than 10,000 times fainter than Alpha Centauri A sitting right beside it, in principle. The reality, as the 2023 observations made painfully clear, involved 2 separate complications that the team had to solve before any science could be extracted. The first was pointing stability. The 4QPM requires the target star to be positioned at the exact centre of the mask, with an accuracy of better than about 10 milliarcseconds. This is an almost incomprehensibly small angular tolerance. To put it in scale, 10 milliarcseconds is the angle subtended by a human hair, viewed from approximately 60 kilometers away. Achieving this alignment requires a precise offset from a nearby bright guide star, and because Alpha Centauri is moving rapidly across the sky, it has a proper motion of about 3.7 arcseconds per year. The guide star acquisition must account for the ongoing differential motion between the telescope, the Sun, and the target system. The first attempt in 2023 failed partly because this offset procedure had not been sufficiently validated for a target of this brightness and motion. The second complication was Alpha Centauri b. When the coronagraph successfully suppresses Alpha Centauri a, it does nothing whatsoever to suppress Alpha Centauri b, which is sitting somewhere between 7 and 8 arcseconds away on the detector, unocculted, blazing at full infrared brightness, contaminating the exact region of sky where a planet around Alpha Centauri a might be hiding. The diffraction pattern of Alpha Centauri b is not a simple ring that can be subtracted with a standard template. It is a complex asymmetric pattern that changes position and orientation with every epoch of observation because the two stars are in mutual orbit and their angular separation changes over the years-long arc of their 79.91-year orbital period. The team's solution was methodologically beautiful and technically formidable. They used a technique called reference star differential imaging, or RDI, observing a carefully chosen reference star, in this case Epsilon Muscae, using the same coronagraphic setup as the Alpha Centauri A observations, and then subtracting the reference star's PSF from the science data to remove the residual diffraction pattern of Alpha Centauri A. For Alpha Centauri B, they observed Epsilon Muscae again, but this time at the off-axis position on the detector where Alpha Centauri B falls, obtaining what amounted to a reference template for the contaminating companion's point spread function, which could then be subtracted separately. This dual subtraction approach had never been applied to an astrophysical scene this complicated. It was essentially a new technique developed specifically for this target. What it required in practice was an observation sequence of extraordinary complexity. For each epoch, the team needed a coronagraphic observation of Alpha Centauri A, a small grid dither observation of Epsilon Muscae as an on-axis PSF reference, and an off-axis observation of Epsilon Muscae at the position of Alpha Centauri B as a companion PSF reference. Each of these required its own detailed calibration, its own timing, and its own allocation of telescope time. The total observation duration per epoch, including the Alpha Centauri A science frames and the Epsilon Muscae reference frames, ran to roughly 9,287 seconds per roll angle for the science target, approximately 2.5 hours per pointing, not counting calibrations, guide star acquisitions, and instrument settle times. This is all by way of explaining that when, in August 2024, the team finally obtained their first clean dataset and loaded it into the analysis pipeline, running the subtraction algorithms, applying the KLIP code, the Kahunen-Loewe image processing algorithm, a powerful principal components-based method for suppressing residual stellar light. The appearance of S1 in the cleaned image was not something that made anyone immediately reach for a champagne bottle. It made them reach for their error budget's S1. The designation is about as clinical as science gets. It stands within the paper for Source 1, a faint orange blob at the 9 o'clock position relative to Alpha Centauri A in the processed MIRI image, detected at a signal-to-noise ratio of between 4 and 6 standard deviations. Its flux density in the F1550C filter, the 15.5 micron passband of MIRI's coronagraph, was approximately 3.5 millijanskis, corresponding to a contrast ratio of roughly 5 times 10 to the power of -5 relative to the star itself. It was sitting at a projected separation of approximately 1.5 arcseconds from Alpha Centauri A, corresponding, at the known distance of 1.34 parsecs, to a physical separation of approximately 2 astronomical units. Before any claim about the nature of S1 could be made, the team had to rule out every alternative explanation for its existence. Was it a detector artifact? Unlikely. The team conducted injection recovery tests, artificially introducing fake sources of known brightness into the raw data and recovering them through the pipeline, and found that the location and flux of S1 were consistent with a real astrophysical source, not a processing artifact. Was it a PSF subtraction residual, a ghost created by imperfect removal of one of the two stars' light patterns? The team ran multiple independent subtraction algorithms and found S1 persisting across all of them. Was it a background galaxy caught behind the stars? Background sources have known statistical distributions on the sky, and at the position and brightness of S1, the probability of a background galaxy coincidentally sitting within the science region was calculated to be extremely low. The team used archival catalogue data and proper motion arguments to eliminate this possibility with high confidence. Was it an asteroid from within our own solar system passing through the field? Asteroids move. S1 did not exhibit the arc of motion expected from a foreground solar system body during the observation period. The team went through the checklist with the methodical thoroughness that this kind of claim demands. And at the end of the checklist, S1 remained, unexplained by any contaminant they could identify, consistent with, though not definitively proven to be, a planet orbiting Alpha Centauri A, and then they took their follow-up observations in February 2025 and April 2025, and S1 was gone. This is the moment where the story becomes genuinely unsettling in the most scientifically productive way possible. The detection had seemed so promising. The statistics had been clean, the alternative explanations had been systematically defeated, and now the object had simply vanished from 2 consecutive follow-up observations, 6 months apart, taken with the same instrument, the same coronagraphic strategy, the same reference star, the same pipeline, a disappearing planet. I want to be precise about what the team did next, because it represents some of the most careful and honest scientific reasoning I have encountered in recent planetary science literature. Rather than declaring S1 a false alarm and withdrawing the claim, which would have been one reasonable response, or insisting on its reality without accounting for the non-detections, which would have been the opposite irresponsible response, the team ran simulations, millions of them. They used orbital dynamics code to model every plausible trajectory that a Saturn mass body orbiting Alpha Centauri A in the range of 1 to 2 astronomical units could follow, subject to the gravitational perturbations of Alpha Centauri B, and constrained by the historical dynamics of the binary system. They then asked, of all those possible orbits, what fraction would produce a detection in August 2024 at the location and brightness of S1, while also being undetectable in February 2025 and April 2025? The answer was roughly half of them. In approximately 50% of the orbital configurations that were dynamically stable in the presence of Alpha Centauri B, a Saturn mass planet could have been in the right location to appear as S1 in August 2024, and subsequently moved to within the coronagraph's inner working angle, the zone of suppression immediately surrounding the star, by the time of the February and April follow-ups. In other words, the disappearance was expected. The planet, if real, was simply hiding behind the light. This is the disappearing world problem, and it is not a problem in the sense of a failure. It is a problem in the sense of a puzzle that has a solution and a testable prediction embedded within it. Let's talk about what S1 is, if it is what the team thinks it is. The photometry, the measurement of S1's brightness in the 15.5 micron bandpass, yields a flux density of approximately 3.5 millijanskis. To translate this into a physical description of a possible planet, the team used planetary evolution and atmosphere models that relate a body's mid-infrared emission to its radius, mass, age, and effective temperature. The age of the Alpha Centauri system is estimated at 5.3 billion years, comparable to but slightly older than our own solar system's age of approximately 4.6 billion years. At 5.3 billion years of age, a gas giant that formed in the system's early history and has been slowly cooling ever since would have an effective temperature somewhere in the range of 300 to 500 Kelvin, depending on its mass and formation history. A planet at 300 Kelvin, at the distance of Alpha Centauri, would emit mid-infrared flux at approximately the level observed for S1 if it had a radius of between 1 and 1 times the radius of Jupiter, or between 11 and 12 Earth radii. The corresponding mass estimate drawn from the planetary evolution models, falls in the range of 90 to 150 Earth masses, or equivalently 0.28 to 0.47 Jupiter masses. That puts it squarely in the Saturn mass regime, too small to be a brown dwarf, clearly in the planetary category, but a gas giant. Not the kind of rocky, Earth-like world that anyone's gut hopes to find around a nearby star. Its proposed orbit is elliptical, with a semi-major axis varying between 1 and 2 astronomical units from Alpha Centauri A, the habitable zone of Alpha Centauri A, defined as the range of distances at which stellar irradiation would support liquid water on a rocky surface under Earth-like atmospheric conditions, sits at approximately 1.27 astronomical units, given the star's luminosity of about 1.509 times the Sun's. This means that S1, if it is real and orbiting as the models suggest, is spending at least part of its elliptical journey within Alpha Centauri A's habitable zone. Not all the time. The elliptical orbit swings it between roughly Venus orbit proximity and beyond Earth orbit distance, but for significant fractions of its 2 to 3 year orbital period, it is there. This is, to my mind, one of the most remarkable specificities in the entire discovery. The fact that what Webb found is not in a remote, harsh region of the system, but in the habitable zone itself, the single band of orbital real estate that we consider most auspicious for life, is a detail that cannot be treated as incidental. Now, a gas giant in the habitable zone is not itself habitable, at least not to anything we currently recognise as life. The atmospheric pressures at depth in a Saturn-mass planet would be in the millions of atmospheres. The temperature gradient from cloud top to interior extremes is enormous. There is no stable surface, no liquid water ocean on which biochemistry could organise and diversify over geological timescales. The planet itself, if it exists, is not a place for life, but this is where the orbital mechanics of moon formation become deeply relevant, and where the question opens rather than closes. Saturn's moon Titan, the second largest moon in our solar system, has a dense nitrogen atmosphere, surface lakes and rivers of liquid methane, and organic chemistry of a complexity that has occupied prebiotic chemists for decades. Titan is not at the habitable zone of the Sun, but it manages, because Saturn's tidal heating and atmospheric insulation give it conditions unlike anything else we know. An exomoon orbiting a Saturn-mass planet at Alpha Centauri's habitable zone would receive approximately the same stellar flux as Earth receives from our Sun. It would have access to tidal heating from its parent planet. It would have the gravitational shield provided by a large planet companion, which is one of the mechanisms thought to have helped stabilise Earth's climate over geological time by reducing the frequency of large asteroid impacts. These are not trivial advantages for an environment seeking to sustain biology. The scientific community has been modelling exomoon habitability for years, largely as a theoretical exercise, because no confirmed exomoon has ever been found. The discovery of a gas giant in Alpha Centauri A's habitable zone would not be evidence for life, but it would be something arguably more powerful. It would be the first concrete, observationally grounded reason to ask whether any of its potential moons could be habitable. And it would be asking that question about a system 4.37 light-years from our Sun. There is also something else the numbers are telling us that the popular accounts have somewhat underplayed. The brightness of S1 in the 5 micron band is not the same as the brightness of the 2019 VLT NIA candidate C1. The two detections, separated by 5 years, 2 different telescopes, 2 different wavelength regimes, 2 different imaging methodologies, are not perfectly identical in their inferred properties. C1 was estimated to be roughly consistent with a planet of at least 3.3 Earth radii at 300 Kelvin, which is compatible with the S1 mass radius estimates, but not exactly constraining. However, both detections sit at projected separations of roughly 1 to 2 astronomical units from Alpha Centauri A. Both are in the habitable zone or its immediate vicinity. Both are in the thermal infrared. And critically, C1 was found on one side of the star in 2019, while S1 was found on the approximately opposite side of the star in 2024. If those two objects are the same body orbiting with a period of approximately 2 to 3 years, then in the 5 years between the detections, roughly 2 to 3 full orbital cycles, the geometry of visibility from Earth would place it near the 2019 position in one observation season and near the 2024 position in another. Kevin Wagner of Steward Observatory, who led the 2019 Naye study and contributed to the 2025 Webb analysis, put it with characteristic restraint. When all you have is a dot of light next to a star, you may or may not be looking at an actual planet. But when you see a dot of the same brightness several years later on the opposite side of the star, the story becomes much more compelling. 2 independent instruments, 2 independent methodologies, 2 independent teams, 1 candidate, appearing on roughly opposite sides of the same star, separated by approximately 5 years, consistent with the orbital period of a gas giant. This is not proof. Science requires more than consistency. It requires confirmation, reproducibility, and the elimination of all alternatives. But it is exactly the pattern that a real planet would produce. And that combination of facts, taken together, is why Kevin Wagner called this one of the most exciting results in astronomy of the decade. But the analysis reveals something else, something that the papers acknowledge, but that I think deserves to sit in the foreground rather than the footnotes. Running simulations of millions of possible orbits under the gravitational dynamics of the Alpha Centauri binary system reveals that the stable zone for planetary orbits around Alpha Centauri A, the region where a planet would not be gravitationally disrupted by Alpha Centauri B over long timescales, is limited to separations of roughly 3 astronomical units and closer. Beyond about 3 astronomical units, Alpha Centauri B's periodic gravitational perturbations will, over millions of years, destabilize any planetary orbit, pumping energy into it until the orbit becomes too eccentric and the planet is either ejected from the system or flung into the parent star. This is the stability boundary, and S1, if real, sits comfortably inside it, but only just, which means that if this planet formed where we currently observe it, it did so in a system that was, from the moment of its birth, under constant gravitational duress. Planet formation in binary star systems is not merely complicated. It is, according to certain formation models, nearly prohibited under the conditions that prevailed in the early Alpha Centauri system. The eccentricity of the binary orbit means that at certain points in the binary's history, the gravitational stirring by Alpha Centauri B would have been intense enough to prevent planetesimals in the inner disk from gently accreting into a planet, instead shattering them on impact. This is the formation paradox of Alpha Centauri, and it is the third open question that runs through every layer of this discovery. If the gravitational environment of this binary system should have prevented planet formation around either star, how is there apparently a planet there? Among the 11 co-authors on the 2 papers published in the Astrophysical Journal Letters, under the collective title Worlds Next Door, one name sits in the co-first author position in a way that tells a particular story, not just about the discovery itself, but about what it means to dedicate years of a young career to an observation that might yield nothing. Aniket Sanghi was a third-year PhD student in astrophysics at the California Institute of Technology when the August 2024 observations were taken. An NSF graduate research fellow, he graduated summa cum laude from his undergraduate institution before beginning his doctoral work at Caltech's Cahill Center for Astronomy and Astrophysics, an address that carries weight in the world of observational astronomy. He is, by the metrics of academic science, at the very beginning. He is also, as of August 2025, the co-first author of a paper that may describe the most important extrasolar planet candidate ever found. The observation itself took place in the small hours of an August night in 2024, though night, for a space telescope in a halo orbit around the L2 point 1.5 million kilometers from Earth, is a somewhat notional concept. JWST does not sleep. It does not wait for darkness. It pivots between targets continuously, executing the hundreds of observing programs approved by the scientific community in each cycle of its operation. The Alpha Centauri observation, part of a Cycle 1 General Observer Program, Program ID 1618, led by PI Charles Beichmann with co-pi Dimitri Mouet, was one among hundreds. Webb turned, locked its guide stars, confirmed the acquisition of Alpha Centauri A behind the 4-quadrant phase mask, and began its integration sequence of 1,250 frames. The data were not analysed in real time. JWST does not call its astronomers with immediate updates. The raw files were stored on board, transmitted to the ground station in Malindi, Kenya, or the White Sands Complex in New Mexico, as part of the telescope's regular downlink schedule, processed through the automated pipeline, and made available for download from the Mikulski Archive for Space Telescopes. Sanghi and the team received the raw calibration files, began the intricate sequence of pre-processing steps: bad pixel correction, background subtraction, PSF modelling, the full stack of the data reduction pipeline they had spent months refining, and worked through the analysis over the days and weeks following the observation. There is a moment in that process, and anyone who has ever worked with astronomical data will recognise it, where you load the final reduced image for the first time. After all the corrections, all the subtractions, all the algorithm passes, you look at what is left. Usually what is left is noise. Noise is almost always what is left. This is what most nights of astronomical observation produce: a cleaned image with nothing unexpected in it. An absence of signal is not failure in science, it is information. An absence of signal tells you something about how rare the things you are looking for must be. But sometimes, very rarely, what loads onto the screen is something else. A point source. A dot of light where there should not be a dot of light, sitting at a separation and position angle consistent with what you were looking for, at a brightness that falls within the range of theoretical prediction, not a smear or a ring or an obvious artifact, but a dot. Clean, localized, faint and stubbornly present across multiple independent reductions of the same data. S1 was that dot. I would give a great deal to know what Aniket Sanghi thought in the specific second that object first appeared on his screen. Science trains you to suppress the emotional response in favour of the skeptical one. The first thing a rigorous astronomer does upon seeing an unexpected signal is not celebrate, but reach for the list of reasons it might not be real. Artifact? Run the injection recovery tests, PSF residual. Run the alternative subtraction algorithms. Background object? Check the catalogue data. Asteroid? Check for motion. The celebration, if it comes at all, comes much later, after the skeptical tests have been exhausted and the object persists, still unexplained, still there. What I do know is that the subsequent months were not comfortable ones for the team. The object needed follow-up. The science team, led by Beichmann, applied for director's discretionary time at the Space Telescope Science Institute, a special allocation of JWST observing hours that bypasses the normal competitive proposal process and is granted in cases of urgent scientific need. DDT is not freely given. It requires a compelling case that the observation cannot wait for the next regular cycle, that it would be scientifically catastrophic to delay, and that the immediate investment of rare telescope time will yield commensurate returns. The case for Alpha Centauri follow-up was approved, twice, for the February and April 2025 observations, which tells you something about how seriously the community took the August 2024 detection. February 2025 came. The team pointed JWST back at Alpha Centauri A, executed the same coronagraphic strategy, the same reference star approach, the same pipeline, and S1 was not there. This is the moment when, for many scientists, the emotional trajectory of a discovery story becomes genuinely difficult to characterize. The obvious human reaction is devastation. You found something remarkable, you spent months building the follow-up case for it, you got the precious telescope time to confirm it, and the thing is gone. But Sanghi and Beichmann and the team did something that speaks to the quality of their scientific thinking. They did not declare defeat. Instead, they read the absence of a signal as data, and they ask what that data implied. What it implied in the context of the orbital simulations was actually encouraging. The simulations showed that if S1 were a planet on an orbital period of 2 to 3 years, its elliptical trajectory would carry it behind the star's coronagraphic inner working angle, the zone of maximum suppression immediately surrounding the stellar position. For significant fractions of its orbital phase, a planet that was visible in August 2024 at 2 astronomical units projected separation could plausibly be invisible in February 2025, not because it had disappeared, but because it had moved to a position less than about 0. 7 arcseconds from the star, inside the mask's suppression zone, effectively hidden by the very instrument trying to find it. The planet in this scenario was not gone. It was behind the star's light, hiding. This interpretation required one more piece of information to become viable: the 2019 VLT detection of C1. When the team incorporated C1's position, brightness, and timing into the orbital simulations alongside S1, the number of dynamically plausible orbits that could explain both detections narrowed considerably. And those orbits made a prediction: the planet, travelling its elliptical path, would next be in a position accessible to Webb in approximately August 2026, one full orbital cycle after the August 2024 detection. As Kevin Wagner told the University of Arizona Communications Office after the papers were accepted, the observations and orbital simulations provide us with a prediction for where the planet will be in the future, and the best time for us to go back and look at it will be in fall of next year. He was referring to fall of 2026, that date that predicted return of a World 41. 3 trillion kilometres from our Sun is where the empirical story currently sits, not at confirmation, not at certainty, but at a prediction that is, in the language of Popperian philosophy of science, falsifiable. In fall 2026, either S1 will reappear at approximately the predicted position, in approximately the predicted brightness, and the scientific community will have the confirmation that transforms a candidate into a discovery, or it will not appear, and the 2 independent detections from 2019 and 2024 will join a growing list of intriguing signals that the universe declined to elaborate upon. There is something both exhilarating and quietly terrifying about that kind of waiting. Every active observational astronomer knows it. The universe holds your hypothesis for months or years before it agrees to give you an answer. Aniket Sanghi's PhD committee at Caltech will almost certainly include among its members people who lived through the Alpha Centauri BB retraction in 2012, who know in their bones the cost of premature certainty in this field. He himself, in his public-facing communications about the discovery, has been scrupulously careful, a planet candidate, not a confirmed discovery, in a way that reflects both his training and, I suspect, a hard-won emotional discipline about the gap between what you want to be true and what you have proven to be true. But here is what I find genuinely moving about his situation, and about the situation of every early career scientist who stakes the formative years of their professional life on a single high-stakes observation. The willingness to be wrong is not a weakness in science. It is the mechanism by which science works. Sanghi put his name on a result that might not be confirmed for 2 years, in a field with a memory long enough to recall what happened to the last major Alpha Centauri planet claim. That takes a particular kind of intellectual courage, not the dramatic kind of courage that shows itself in crises, but the quiet, daily kind that consists in saying, "Here is what I found, here are the reasons to believe it, and here are the reasons to doubt it, and I am prepared to be judged by what August 2026 shows." The universe, indifferent as ever to our need for tidiness, offers no guarantees. Let's talk about what is actually at stake here, because I think the way this story has been covered in the popular science press has consistently underestimated it. The typical framing goes something like this: astronomers may have found a planet around the nearest star system. It is a gas giant and therefore not habitable, but it's still exciting because it's nearby. This framing is accurate, but it is about as revealing as describing the Apollo 11 mission as a trip where some Americans went quite far from home and came back safely. What is actually at stake is the rewriting of our baseline expectation for how common planetary systems are, and specifically for how common planetary systems are in the kind of gravitationally complex environments that characterize the majority of stellar systems in the galaxy. Here is a number that does not get enough attention in the mainstream discussion of exoplanet science. Approximately 50% of solar-type stars in the Milky Way exist in binary or multiple star systems. Not a minority, not an exotic edge case. Roughly half of all stars like our Sun have a companion. And yet, because planet detection is so much harder in binary systems than around isolated stars, the gravitational complexity, the contamination from the companion's light, the difficulty of modelling stellar activity, with a second star perturbing the dynamics. The overwhelming majority of the roughly 800 confirmed exoplanets, known as of 2025 orbit single stars. Our sample is radically biased toward the kind of star we find easiest to study. The discovery of planets around Alpha Centauri A, if confirmed, would represent the first compelling direct imaging detection of a planet in the habitable zone of any binary stellar system. The significance of that goes beyond the specific case of Alpha Centauri. It would provide empirical grounding for the theoretical models, suggesting that stable planetary orbits can form and persist within binary systems under the right conditions, and it would force a reassessment of how aggressively we should be searching for planets in the billions of binary systems distributed across the Milky Way. More immediately, it reframes the statistics of planetary habitability in our immediate cosmic neighbourhood. Within a sphere of 10 light-years around our Sun, there are 12 known stellar systems containing a total of approximately 18 stars. Alpha Centauri at 4.37 light-years is the nearest. Barnard's star at 5.96 light-years is the second. Wolf 359 at 7.78 light-years is the third, and so on. Most of these systems are red dwarfs, smaller, cooler, dimmer, and in many cases far more magnetically violent than our Sun. Alpha Centauri A is the only star within this 10 light-year bubble that is genuinely Sun-like in terms of spectral type, luminosity, age, and the stability of its radiation environment. If Alpha Centauri A has a gas giant in its habitable zone, the implications for planetary formation theory are significant. Gas giants in habitable zones are not, in themselves, common in the exoplanet catalogue. We have found thousands of hot Jupiters, gas giants hugging their stars at orbital distances of a few hundredths of an astronomical unit, scorched to temperatures of 1, zeros and Kelvin and above. Because the transit method that produced most of our exoplanet detections is most sensitive to large planets in short orbits, but cold gas giants, like Jupiter and Saturn in our own solar system, orbiting at 1 to 5 astronomical units in the habitable zone and beyond, are far harder to detect with the currently dominant methods and far less well characterized. S1, if confirmed, would be the first cold gas giant imaged directly within the habitable zone of any star. The first one we could actually look at and take spectroscopic measurements of. This would become a touchstone object for exoplanet science, said Beichmann in the NASA press release, with multiple opportunities for detailed characterization by Webb and other observatories. He was being, if anything, understated. A confirmed gas giant in the habitable zone of the nearest Sun-like star would be the most characterizable planetary body outside our own solar system by an enormous margin, because of the inverse square law of light. The fact that the brightness of any object decreases with the square of the distance. A planet at 4.37 light-years is about 280 times closer than a planet at a typical target distance of 50 light-years. That factor of 280,000 in distance translates to a factor of roughly 78 billion in the number of photons arriving at our detectors. Every measurement of composition, temperature, cloud structure, molecular absorption features in the atmosphere, everything we want to know about a planet becomes dramatically more tractable. And then there is the question of moons. This is where I want to be careful, because the scientific literature on exomoon habitability is genuinely hypothetical. No exomoon has been confirmed, and claims of exomoon candidates in the literature have so far failed to survive rigorous scrutiny. But the theoretical case is well established and deserves to be stated clearly. A gas giant in a habitable zone will, if it resembles giant planets in our own solar system in terms of moon-forming potential, host a system of satellites. In our own solar system, gas giants have enormous moon families. Jupiter alone has 95 confirmed moons, Saturn 146. The large moons, Europa, Ganymede, Titan, Enceladus, are among the most astrobiologically interesting objects in the solar system. Europa and Enceladus likely have subsurface liquid water oceans in direct contact with rocky floors, creating the chemical gradients that many origin of life researchers consider necessary for prebiotic chemistry. Titan has a methane-nitrogen atmospheric cycle of astonishing complexity. These moons are interesting despite their distance from the Sun's habitable zone because they have other energy sources, primarily tidal heating from their parent planets, supplementing the reduced solar flux they receive. Now move the parent giant planet into the habitable zone. Give the moons the same tidal heating they would have around any gas giant, plus full stellar irradiation at Earth equivalent levels. The energy budget for potential life on such a moon becomes not merely adequate but generous. This is not a prediction. This is a theoretical possibility made suddenly concrete by the existence of S1, and the concreteness of it, the fact that we can now point at a specific real candidate object in a specific habitable zone at a specific distance and say there, that thing, its moons might be habitable, is a transformation in the character of astrobiology, not a change in our knowledge, a change in our relationship with a question, but the stakes extend even further into a territory that planetary scientists are still grappling with. The question of what the existence of S1 implies for the orbital history of the Alpha Centauri system, and specifically for the possibility of rocky terrestrial planets also existing around Alpha Centauri A. If S1 is real and orbiting at 1 to 2 astronomical units, it cannot exist in isolation. Its gravitational influence on the surrounding disk of material during the system's formative period would have been profound. Gas giants in this mass range are not passive occupants of their systems. They actively sculpt the distribution of smaller bodies through gravitational resonance effects, creating clearing zones, shepherding material, deflecting smaller bodies into and out of the inner system. Whether that sculpting process would have enhanced or suppressed the formation of smaller rocky planets closer to Alpha Centauri A. Within 1 astronomical unit, a terrestrial worlds might form, is a question that goes to the heart of what we think we know about planetary system assembly. In our own solar system, the current favoured hypothesis, the so-called Grand Tack model and its successors, holds that Jupiter's early inward migration to approximately 1.5 astronomical units and subsequent outward migration under Saturn's gravitational influence was instrumental in depleting the inner solar system of the planetesimal material that would otherwise have built a much more massive set of inner planets. Earth's mass under this model is partly a consequence of Jupiter's disruptive presence. Too much disruptive migration and you lose your inner rocky planets. Too little disruption and you end up with an overstocked inner system where collisional erosion prevents stable worlds from forming. S1 represents, if confirmed, a case study in whether this kind of gas giant architecture replicates itself in other solar mass stars in similar gravitational environments. The answer will take years to disentangle, but the first question, is there a gas giant, is apparently being answered now, which brings us to the question that haunts every layer of this narrative. If the answer is yes, if there is a Saturn mass gas giant in the habitable zone of Alpha Centauri A, what else is there in that system? What didn't Webb find? Here is something about the Alpha Centauri observations that I think deserves more attention than it typically receives, and it is this. The fact that Webb found something is not the most scientifically significant result from these observations. The most scientifically significant result is that Webb found something and simultaneously placed the deepest constraints on what else might be there. This requires some explanation. Naye's coronagraphic observations of Alpha Centauri A in August 2024 achieved what the technical papers describe as a typical 5 sigma point source contrast sensitivity between approximately 10 to the power of -5 and 10 to the power of -4 at separations greater than 1 arcsecond. In plain language, at separations of more than about 1 arcsecond from Alpha Centauri A, corresponding to approximately 3 astronomical units at the star's distance, Webb would have been able to detect any point source more than 10,000 to 100,000 times fainter than the star itself, which translates to planets with radii larger than approximately 5 Earth radii and temperatures warmer than approximately 300 Kelvin. That sensitivity did not reveal a Jupiter-mass planet. It did not reveal a 10 Earth radius super-Neptune. It revealed one candidate, S1, at the stated brightness and nothing else. The upper limit on the presence of additional giant planets in that region of the system is now, for the first time, truly meaningful, and the absence, the carefully characterized, quantified absence of larger bodies, is itself scientifically powerful. It constrains the parameter space for what kinds of planetary architectures can exist around Alpha Centauri A, a Jupiter-mass planet orbiting at 2 astronomical units at the system's age and distance would be significantly brighter in the mid-infrared than S1. Webb would have found it if it were there. It was not found. Therefore, to within the sensitivity limits of these observations, there is no Jupiter mass or larger body in the observable range of the search. This matters enormously for the habitability question. One of the most consistent findings of exoplanet science over the past 15 years is that the presence of a Jupiter-mass planet in a system's outer regions appears to correlate with the presence of smaller, rocky worlds in the inner system, a relationship sometimes called the architectural correlation. Though it remains debated in its details, the absence of a truly massive Jupiter-class or above disruptor in the Alpha Centauri, a system above the sensitivity threshold of these observations, is consistent with a scenario in which a less massive Saturn-class planet occupies the habitable zone without having cleared out the inner system entirely. Whether that leaves room for rocky, Earth-mass planets closer to the star, inside perhaps all 0.5 astronomical units, where the coronagraph's inner working angle prevents even Webb from currently seeing, is a question that will require very different instrumentation to answer. Let's also address the exozodiacal dust result, because it is, in the context of the broader search, extraordinary. One of the other questions this program was designed to answer was not about planets at all, but about dust, specifically the density of microscopic silicate and carbonaceous particles in the habitable zone of Alpha Centauri A, produced by collisions among asteroid-like bodies and organized into a disk by the star's radiation pressure and gravity. In our own solar system, this disk of dust, known as the zodiacal cloud, contributes a faint glow to the night sky, sometimes visible to the naked eye under the best conditions. In systems with active collisional debris disks, this emission can be vastly brighter, potentially swamping the signal of any planets embedded in it, and even absorbing and re-emitting enough stellar radiation to alter the thermal environment of any habitable zone worlds. Webb's observations placed an upper limit on the density of exozodiacal dust around Alpha Centauri A of approximately 1 times the density of our own solar system's zodiacal cloud. In the literal language of the papers, this is the deepest sensitivity to exozodiacal disks achieved for any stellar system to date. No other instrument, before this observation, had been able to search for the zodidust equivalent of our own solar system around any other star. Every previous upper limit had been considerably higher, meaning that, until 2024, we could not rule out that Alpha Centauri A was surrounded by a dust disk 10 or 50 or 100 times denser than our own, which would have enormous implications for the thermal environment and the visibility of any planets. The new limit says The Zodi dust, if it exists, is no denser than what we see in our own solar system. Alpha Centauri A's habitable zone is, as far as this technique can determine, relatively clear. This is another deeply consequential non-detection. It means that the inner regions of Alpha Centauri A's system are not shrouded in obscuring material. It means that future telescopes attempting spectroscopy of any candidates, measuring the molecular fingerprints in reflected or emitted light, would not be fighting through a dense curtain of re-radiating dust. It means that if there are planets there, we have a fighting chance of characterizing them. But let's return to the deeper question of what these data tell us, and what they don't about the system's overall architecture, because this is where the story acquires what I consider its most genuinely troubling dimension. The Alpha Centauri binary pair, Alpha Cyn A and Alpha Cyn B, orbit each other with a period of 79.91 years and an eccentricity of 0.52. At their closest approach, called periastron, they are 11.2 astronomical units apart. At their furthest, apastron, they are 35.6 astronomical units apart. The dynamical stability calculations, updated and refined over decades, suggest that stable prograde orbits around Alpha Centauri A are possible for separations up to approximately 3 astronomical units. Beyond that, the eccentric companion's periodic gravitational kicks will, over millions of years, excite orbital eccentricities in any orbiting bodies until they become unstable. The stable zone is not tiny. It is actually comparable to the inner and middle regions of our own solar system, but it is definitively bounded by the presence of B. Planet formation in this environment presents a genuine theoretical challenge. The classical core accretion model for giant planet formation requires that small bodies, planetesimals, typically a few to 100 kilometers in diameter, accumulate through relatively gentle collisions into ever larger protoplanetary cores, until a core reaches perhaps 10 to 15 Earth masses and is able to gravitationally capture the surrounding gas disk. The timescale for this process in the nominal model is millions to tens of millions of years, and the problem in a binary system with an eccentricity of 0.52 is that the periodic gravitational perturbations from the companion star drive up the relative velocities of the planetesimals, not enough to prevent collision, but enough to ensure that collisions between same-sized bodies are often destructive rather than accretive. You build up, you get smashed back down. Planetesimals fragment before they can grow. Several theoretical groups have tried to resolve this through modifications to the classical picture. One approach involves invoking an early phase of gas-rich disk dynamics that damps the eccentricity of the planetesimal swarm before the gravitational kicks from the companion fully develop. Another involves considering the possibility that planetesimals don't need to form locally, that S1, if it is a real planet, may have formed further out in the system's original disk and subsequently migrated inward to its current orbit through interactions with the gas. A third approach questions whether the initial disk of the Alpha Centauri system was oriented in the same plane as the binary orbit, because a misaligned disk would experience very different perturbation dynamics. None of these solutions is settled. Each comes with its own set of problems and assumptions. The formation of a Saturn-class planet at 1 to 2 astronomical units in the Alpha Centauri system is not readily explained by any single model. The Astrophysical Journal Letters papers acknowledge this directly. Its very existence in a system of 2 closely separated stars would challenge our understanding of how planets form, survive, and evolve in chaotic environments. Challenge, in scientific language, is a specific kind of word. It does not mean contradict or refute. It means create productive tension with, requiring revision. The detection of a planet where models suggest planet formation is difficult does not prove the models are wrong. It suggests they are incomplete, or that there are pathways to planet formation in binary systems that we have not yet identified. Finding those pathways, building the models that explain how S1 got to where it apparently is, will occupy theoretical planetary scientists for years. It is the kind of problem that generates dissertations. There is a deeper layer of unease here too. which I think gets at why this discovery feels specifically disturbing in the way the original topic title suggests. It is not that finding a planet around the nearest star is frightening in any visceral sense. It is that the implications accumulate so quickly and so inexorably that they begin to change the shape of the question we thought we were asking. We have been searching for Earth-like planets around nearby stars as a way of establishing whether we are alone. The logic is, if we find something Earth-like near us, the implication is that Earth-like worlds are common and that life, wherever it originates, has many possible homes. This is the motivating philosophy behind missions like Kepler-TESS, the search for Earth-mass planets in the habitable zones of nearby red dwarfs. It is also the motivating philosophy behind a half-century of SETI research, and behind the implicit assumption embedded in the Drake equation that the emergence of life depends partly on the abundance of habitable environments. But the Webb result complicates this in a specific way. The nearest star system, the one we have used as our symbolic first destination, the one that has stood for decades as the nearest possible outpost of life beyond our own world, that system apparently has a gas giant in its habitable zone, not an Earth, not even a super-Earth, a gas giant, which may or may not have moons, which may or may not be orbited by bodies capable of sustaining liquid water, and whose very presence changes the gravitational history of the system in ways we do not yet fully understand. The question we thought we were asking, is there a world like Earth near us? Turns out to have yielded, as its first concrete empirical answer, there is a world like Saturn near us. The answer is not wrong. The answer is different. And the difference between Saturn-like and Earth-like, in the context of what we were hoping to find, is the difference between a promising lead and a redirection. This is not cause for despair. I want to be clear about that. The fact that our nearest neighbour may harbour a gas giant rather than a rocky world tells us something enormously valuable about how planetary systems form and evolve in diverse stellar environments. It tells us that the habitable zone can be occupied by architectures we did not anticipate. It generates predictions about moons. It challenges the models in productive ways. It gives future telescopes a specific, close, bright, and well-characterized target to investigate. But it does also raise a question that I find genuinely unsettling in its scope, and it is this. If the nearest star system, the one we know best, the one we have been looking at hardest, the one that science fiction has for decades populated with human cousins and alien civilizations, turns out to be less hospitable to rocky life than we imagined, what does that suggest about the broader landscape of nearby systems? Proxima Centauri, orbiting about 8200 astronomical units from the AB pair, does have a planet in its habitable zone, Proxima b, confirmed by radial velocity in 2016. But Proxima Centauri is a flare star erupting regularly with X-ray and ultraviolet bursts that would strip the atmosphere from any unprotected rocky world on the timescale of millions of years. Proxima b receives between 10 and 60 times more extreme ultraviolet radiation than Earth does from our Sun. It orbits at roughly 0.0485 astronomical units, an orbital period of 11.2 days, putting it so close to the star that, depending on its internal structure and magnetic field, it may be tidally locked, with one hemisphere permanently facing the star and the other facing permanent night. The habitability of Proxima b has not been ruled out definitively, but the picture is not comfortable. The Alpha Centauri system, taken as a whole, presents not a welcoming vista of potential twin Earths, but a complicated, radiation-intense, gravitationally complicated environment where the conditions for life, if they exist at all, exist in forms that bear little resemblance to the tranquil, Earth-like worlds our imagination had prepared us to find. This is, I believe, what the title of this documentary means when it calls this disturbing. Not disturbing in the sense of threatening. Disturbing in the deeper sense, it has disturbed our expectations. It has rearranged the furniture of our assumptions about what waits for us at the nearest stellar address. And it has done so not by delivering bad news exactly, but by delivering complicated news, the kind that requires you to rebuild your mental model of the question from the ground up. The prediction is August 2026. If the orbital simulations are correct, if the two independent candidates, C1 from 2019 and S1 from 2024, are the same object on a 2 to 3 year elliptical orbit, then in approximately August 2026, that object should return to a position accessible to Webb's coronagraph at approximately the same projected separation and on approximately the opposite side of the star from where it appeared in 2024. Webb's team has been granted the time allocation necessary to make the observation. The telescope is operational. The technique has been validated. The question has a scheduled answer. But even before that answer arrives, the next decade of Alpha Centauri science is already being architected, and the scale of what is being planned reveals just how seriously the community is taking this discovery. The first instrument to complement Webb's observations will be NASA's Nancy Grace Roman Space Telescope, currently in the final stages of pre-launch testing and scheduled for launch by May 2027, with teams working toward a fall 2026 launch, potentially overlapping with the critical August 2026 Webb confirmation window. Roman is, in certain respects, a different kind of telescope than Webb, operating primarily in visible and near-infrared wavelengths rather than mid-infrared, and with a coronagraphic technology demonstrator called the coronagraph instrument, specifically designed to advance the techniques needed for direct imaging of planets around nearby stars. Roman's visible light measurements of S1, if they can be obtained, would complement Webb's thermal infrared data in a critical way. Visible light photometry measures reflected starlight, which depends on the planet's albedo, its reflectivity, and its geometric cross-section, while thermal infrared measures the planet's own heat emission. Combining the two gives you constraints on both the planet's size and its temperature, tightening the mass estimates and allowing more sophisticated atmospheric modelling. The extremely large telescope, currently under construction on Cerro Armazones in the Atacama Desert of Chile, a 39, 3-metre primary mirror that will be the largest optical telescope on Earth, is the instrument that many exoplanet scientists regard as the true long-term future of Alpha Centauri planet characterization. The ELT's first-generation instruments include one specifically designed for high-contrast imaging and spectroscopy of planets around nearby stars, METIS, the mid-infrared ELT imager and spectrograph. Pre-launch simulations suggest that METIS on the ELT would be able to detect Earth-sized planets within the habitable zone of Alpha Centauri A, not just Saturn-mass giants like S1, but rocky, potentially terrestrial worlds at the level where liquid water becomes possible. The ELT is expected to achieve first light around 2028, though first scientific results in its full operational configuration will likely come a few years later. When METIS turns toward Alpha Centauri A, it will do so with Webb's 2024 detection in its context. The confirmed or strongly suggested presence of a Saturn-mass planet at 1 to 2 astronomical units will shape how the team models the debris structure, the dynamical environment, and the expected location of any additional, smaller bodies. You don't search a blank slate with an unknown architecture. You search a system with a known occupant and work outward from there, and that leads to the deepest and most consequential question the next decade will attempt to answer. If S1 is confirmed in August 2026, the following questions immediately become tractable, if not immediately answerable. Does S1 have any moons? Direct detection of an exomoon around S1 is beyond any instrument currently operational or in construction. The signal-to-noise requirements are several orders of magnitude beyond current capability. But over the decade following confirmation, the combination of orbital refinement, atmospheric spectroscopy, and photometric monitoring of S1 will begin to constrain the total mass of the object and its tidal environment in ways that make moon detection, at least statistically, approachable. Is there a rocky planet in the inner system of Alpha Centauri A? S1's orbital parameters will, once confirmed, be known precisely enough to model its gravitational influence on any bodies orbiting interior to it. inside about 0.7 astronomical units. The ELT's sensitivity, combined with Webb's deep upper limits on dust density, will make the search for such interior bodies far better constrained than anything previously attempted. Finding a rocky planet in the inner system of Alpha Centauri A, even a planet with no atmosphere, even one tidally locked to the star, would be the single most significant result in the history of exoplanet science. What can the spectrum of S1's atmosphere tell us about giant planet evolution at 5.3 billion years? This is a question of enormous theoretical interest independent of any implications for life. The molecular composition of a Saturn-mass gas giant at 5.3 billion years in the habitable zone of a G2 star with a binary stellar companion at 11 to 35 astronomical units. This has never been measured. The atmospheric chemistry, the ratio of methane to ammonia to water vapour, the cloud structure, presence or absence of photochemical species. All of this represents a data point in the space of giant planet evolution that no current model fully predicts. The first spectrum of S1, if it can be obtained, will simultaneously test atmospheric models, constrain the planet's mass through gravity-sensitive spectral features, and provide the most detailed picture of a non-solar system giant planet in the history of astronomy. Then there is breakthrough starshot, and here the stakes become civilizational rather than merely scientific. The Breakthrough Starshot initiative, announced in 2016 by physicist Stephen Hawking and internet investor Yuri Milner, proposes to send a fleet of gram-scale nanocrafts, postage stamp-sized spacecraft equipped with light sails, to the Alpha Centauri system on a beam of laser light powerful enough to accelerate them to approximately 20% of the speed of light. At that velocity, the crossing of 4.37 light-years would take approximately 22 years. The nanocrafts would have perhaps a few hours of flyby time at the system before their relative velocity carried them past, but in those hours they could obtain images and basic compositional data at resolutions impossible from Earth. The confirmation of a planet in the habitable zone of Alpha Centauri A. The specific target of the most plausible interstellar mission architecture humanity has ever seriously proposed, transforms the scientific case for that mission from "we should go and see if there's anything there" to "we know there's something there, now we need to know what it is." That is not a subtle distinction. The funding and political will require to build a planetary-scale laser array capable of accelerating a nanocraft to 20% of light speed is measurably easier to mobilize when there is a known target waiting at the destination. Every confirmed planet around Alpha Centauri A makes the case for Breakthrough Starshot more compelling by an order of magnitude. There is also a question here about what we don't see, a silence that deserves to be taken seriously. In August 2024, JWST's MIRI coronagraph searched the habitable zone of Alpha Centauri A at the deepest sensitivity ever achieved for any nearby star system. In that search, it found one candidate at the brightness level of a Saturn-mass planet, and it found nothing else. No Jupiter-mass giant, no sub-Jovian body in a different orbital location. The image, after all the subtractions and the careful pipeline processing, was essentially empty except for S1. That emptiness is, in itself, a kind of answer, a negative answer, but one with real information content. The habitable zone of Alpha Centauri A, at the current epoch and at the sensitivity Webb achieved, contains at most one giant planet. It does not contain a system-filling arrangement of multiple giants. This relative sparseness is consistent with either a formation history that produced a single giant rather than the multiple giant architecture of our own outer solar system, or with the dynamical suppression from Alpha Centauri B having cleared out the zone above 3 astronomical units and left only the most stable configurations intact. But it also leaves open, entirely and uncomfortably open, the question of what is inside 1 astronomical unit from Alpha Centauri A, in the region the coronagraph's inner working angle could not reach. Rocky planets at Venus-like or Mercury-like distances from the star would be completely invisible to this program. They would emit primarily in the visible and near-infrared range, at temperatures too high for the miry F155C filter's sensitivity. They would be within the suppression zone of the coronagraph at all orbital phases. They would be detectable only by radial velocity and the radial velocity precision required to find an Earth-mass planet in the habitable zone of Alpha Centauri A, embedded in the complicated noise environment of a binary system, is at the very limit of what instruments like Espresso on the VLT can currently achieve. We do not know if Alpha Centauri A has Earth-like planets. We do not know if it has Venus-like planets, or Mercury-like planets, or any rocky bodies at all in its inner system. JWST's observations constrain the giant planet population with new rigour. They do not touch the question of small planets at all. This is where the deepest vertigo of this discovery lives. We have taken the most powerful infrared space telescope ever built, pointed it at the most important nearby stellar target, achieved the deepest exoplanet sensitivity ever recorded for any nearby system, and found one candidate at one location and silence everywhere else. The silence is informative, but it is not the complete picture. The complete picture requires instruments we are still building, techniques we are still refining, and in some cases, engineering concepts that exist currently only as papers in progress. The universe, characteristically, has answered one question by opening three new ones. The habitable zone of Alpha Centauri A may host a Saturn-mass gas giant. That gas giant may have moons. Those moons may be habitable, and between the gas giant and the star itself, in the region we cannot yet see, may be, for all we know, a rocky world whose existence we have no current means of confirming or denying. 4 light-years is not a comforting distance. I think it is worth being honest about that, because we tend to use the word nearest as if it implies accessible, as if proximity at the scale of interstellar space translates into some version of manageable. It does not. The fastest spacecraft humanity has ever launched, the New Horizons probe, still arcing outward through the solar system at roughly 14 kilometers per second, would take approximately 78,000 years to reach Alpha Centauri. If it were heading there, which it is not, we are looking, in other words, at an object that is unreachable by any technology we currently possess, at a target that may hold the first confirmed planets in our stellar neighbourhood via a telescope that has to perform acrobatics. We never fully anticipated to even see it, and we still don't know if what we found is real. That is the condition of this science, and I find it in the specific way that science makes things beautiful, genuinely stirring. Not because the uncertainty is comfortable, it isn't, but because the uncertainty is honest. Science doesn't hand you clean answers. When the universe hands it complicated questions, it hands you better questions. And the question that Webb has handed us: is there a Saturn-mass planet in the habitable zone of the nearest Sun-like star? And if so, what does that mean for everything that might orbit it? Is a profoundly better question than anything we were equipped to ask about Alpha Centauri 20 years ago. The first Hubble Space Telescope observations of Alpha Centauri, looking for planetary companions in the near-infrared with its planetary camera in the 1990s, could only rule out the presence of brown dwarfs more massive than 40 Jupiter masses at separations greater than 5 arcseconds. The sensitivity limit then was roughly equivalent to searching for a lighthouse by looking for its beam from a moving train during a thunderstorm. The sensitivity limit today, achieved by Webb in the fall of 2024 in one of the most technically demanding observational programs ever executed, is the equivalent of finding a candle beside that same lighthouse, from the same distance, in the same storm. The improvement spans orders of magnitude and capability, and it has taken 3 decades of engineering, optics, detector physics, space systems engineering, and computational image processing to get here. Aniket Sanghi, the PhD student at Caltech, who found S1 in the reduced data, and whose name appears on the papers that will either become foundational documents of exoplanet science or cautionary reminders that the universe sometimes whispers things that aren't there. He is, right now, waiting for August 2026, when the orbital prediction either holds or it doesn't. waiting with the particular quality of patience that this science demands. Not passive, not idle, but active in the sense of running more simulations, refining more models, preparing the instrument strategy for the follow-up observation, thinking through every possible way the next dataset could confound the interpretation and how to handle each case. This is what the work actually looks like. Not the press releases, not the headlines about disturbing findings next to the nearest star. The actual texture of the discovery is slower, more uncertain, more iterative, and more human than the headlines suggest. A graduate student in Pasadena, California, staring at a processed miry image of the nearest star system, trying to determine whether a faint smudge of infrared photons represents the most significant exoplanet detection in the history of astronomy, or a systematic artifact that everyone, including him, will spend the rest of their career being reminded of. The answer is coming. It is coming in approximately 1 year, assuming Webb is operational and the skies of science remain clear. And when it comes, it will not end the story. It will begin the next chapter of it. A confirmation will open the question of moons, of atmospheres, of the inner system's rocky architecture, of what a Saturn-class planet in the habitable zone of a binary system means for the formation theories that underpin our entire understanding of where planets come from and who gets to have them. A non-detection will close this chapter and raise the question of what C1 and S1 actually were, and whether the hunt must continue with different instruments, different wavelengths, different methods. Either way, we are at the boundary of knowing. There is a phrase in the methodology papers, buried in the technical language of signal detection and sensitivity analysis, that I keep returning to. When discussing the candidate S1, Sangi and colleagues write, additional observations with JWST or upcoming facilities are necessary to redetect candidate S1 and confirm its nature as a planet orbiting our nearest solar-type neighbour. Necessary, not merely desirable. Not scientifically interesting. Necessary. We need to know if that dot of light next to the nearest star is a world. We need to know because the answer changes the map of what our cosmic neighbourhood contains, the map of where habitability might exist, the map of where a light sail probe, launched decades from now by engineers not yet born, should be aimed, the map of what life, if it is not unique to this small, improbably fortunate planet, might be doing right now at the next stellar address over. The universe does not owe us clarity. It has no obligation to place habitable worlds close to us for our convenience, to arrange its planetary systems in configurations that are easy to detect and emotionally satisfying to contemplate. What it has done, instead, is put a faint smudge of infrared light beside the nearest star and left the question of what it means entirely to us, to the instruments we build, to the young scientists who devote their professional lives to finding the answer, to the community that reads the papers, runs the models, argues over the statistics, and eventually, slowly, imperfectly, through the grinding machinery of evidence and doubt and repetition, arrives at something that can be called truth. We are not there yet. Not with Alpha Centauri, but we are for the first time genuinely close.